Welcome to today's Blue Waters webinar. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois. It's our pleasure today to have Galen Arnold talking about Blue Waters performance tools. Galen is a senior systems engineer at the National Center for Supercomputing Applications. Galen, thank you for joining us, and I'll turn it over to you.
All right. Well, we'll get right to it. Today I'll be talking about performance tools, some on Blue Waters and some in the more general case. We'll start with the general case, and I've just got a sort of an outline agenda here to have discussion points. So one of the questions maybe we have in our mind is, what is the point of profiling code? Maybe your code runs and you're getting your work done and you're happy with that. We get this a lot from science teams and people using the system, but I'd like to remind you that we are an HPC system, and the H is not for half, the H is for high performance. And we're all in this together. If you can get more work done in a given amount of time, you'll be more efficient. But not only that, if you can minimize your time on the system, then other people can have more. We're going to start with a classic old school Unix profiling technique. This goes back to Solaris, IRIX, HP Unix, Cray Unix. It's gprof, which grew out of Unix Prof. And the first example here is with SetSM code. SetSM is a code that does 3D elevation models from a stereo pair of satellite photographs. So it's got a lot of geometry and calculations in it. So GNU Prof is a GNU piece of software. It's ubiquitous. You could expect to find it on any kind of Linux. And if it's not there, you can probably get your admin to install it as a RPM or a yum or an apt-get package, whatever is appropriate for that architecture. Also, the compilers will build code for profiling whether you have the gprof tool or not. So we'll get to that in a moment. There are a couple nice URLs here. The one with Lawrence Livermore is a great gprof documentation for an HPC center, and they cover one of the undocumented environment variables that you can use with MPI. I'll leave that for you to look at. The other documentation link here is an old FTP man page about gprof from the GNU project. So one of the big cool things about gprof is that it's a compiler option. You can tell various compilers to build for profiling with the -p or -pg flag, and one of those flags works with just about every compiler. This is kind of standardized like -g is for debugging. So this here is the XL compiler example for an IBM Power system running Linux, but it should work with Intel. Yeah. I'm going to make this a little larger to see. So this should work with Intel or GNU compilers, various compilers. What you're doing when you add this flag is you're telling the compiler and linker to add a library to your code that will do sampling at runtime. So when the code runs, the library jumps in and takes samples of where the code is at some frequency, some regularly scheduled frequency. So you can run an instrumented sampled program on a system, and then you can use gprof on that same system, or if you had gprof on a system with similar architecture, let's say x86-64, you could have that on your laptop Linux and pull the profile and the binary back to your laptop and look at it that way. So it's not even necessary that gprof, the tool, be installed on the machine where you're running it. So here's an example of compiling, and then I ran the code on this system. This was an IBM Power 9. And then that system had gprof on it, so to invoke the profiler and look at the result, I said gprof and then the name of the binary. So after gprof runs, or after your binary runs, a file called gmon.out shows up in the same directory where you ran the code. So let's take a look at the output of gprof. It looks at that gmon.out and your application and uses the data in the gmon.out file and the -pg profile information that was compiled into your application to figure out where things happened and what the sampling summary looks like. My favorite view of gprof is the one we're looking at, which is the flat profile. The flat profile is just a statistical time sampling of which routines consumed the most time, and you'll see that there's some nice fields here, percent time, seconds, and then I also like the number of calls. So you can get a feel for how busy a routine was. So in this code, 2 routines are consuming the bulk of the time. And when we look down through here, we also see some other routines that you might expect from a code that's doing a lot of geometry. Here's the power function. A little further down, sine, arctangent 2, cosine, things that look like they might be doing some sort of geometry, create image pyramid ortho. Now you'll notice the double underscore XLs in front of a lot of these function names. That's because this code was built with the IBM XL compiler. If we'd used Intel or GNU, you might have something different in that location. So that's just an artifact of the flavor of compiler we built the code with. Get a pretty complete listing. Every routine that's sampled is going to show up in that flat profile. And then gprof puts your key explaining what the fields are down below the table. The next one will be call graph. Now call graph shows the routine, but it also shows the things that called it up above and the routines that it called below. This is I don't use this a lot, but this is a handy way to get a feel for what routines call what in your code before you even have to look at the source code. So for this example, I could have compiled a code I'd never seen before and just run it, and I already have some information here now about what the call stack looks like and what routines call each other. gprof includes this so you can get a feel for if a routine is calling something else that's called very frequently. So, for example, vertical line locus is taking up 50% of the time here, but it's also making a massive number of calls to get object to image RPC single. So that might be useful information for you to understand when you're trying to figure out how your code's spending time. And again, there'll be call graph information here for most of the hot routines in the code. Here's the main call graph. further down. Again, I don't tend to use this a lot in my own profiling. I like the first view the best, the flat profile, but this is handy if you're trying to get to know the code before you even open an edit window. Here's your key and explanation further down, below the crawl graph explaining how that works. And then the last part of gprof is just a gprof index number to function name key. And that's my little short intro to gprof. gprof you can expect to work for compiled languages in an HPC system. So C, C++, all the Fortran flavors. If you've compiled it to run, it probably has compiler flags to generate sample profiling data. That's a GNU utility, and you can expect to find it everywhere. So, let's look at some Blue Water specific tools. Why is the Cray so special? I put a little note in here, one of my favorite old slogans, the network is the computer. That was from Sun Microsystems back in the 90s. And it's very true of the Cray. The Cray's network is built into the system. Each of the compute nodes on a Cray has a network card that's specific to the Cray network, but there's not like a hub or a switch. The computer really is the network. And this allows things to work at really large scales. You can run an MPI program with 400,000 ranks on our machine. So that's not an unusual event. Because things can scale so big, Cray has their own tools, and they're very good. And their tools scale. And we're going to take a look at one of those tools next. So this discussion will be about Cray Reveal. And I put the Cray logo up here as a reminder that this is a Cray product. You won't be able to run Reveal on an Exceed Linux cluster like Bridges. You'll need to have a Cray to use this tool. Reveal combines profiling with some automated program parallelization. Now that's been a big wish for decades, that we could somehow magically parallelize a code. And Cray Reveal can actually do some of that for us. And we'll take a look at that here in this demo and walkthrough. So the first steps for using Cray Reveal are to get your modules that you need to use it and do the compilation steps that are required for Reveal. So Reveal is part of Perftools base, and then we also load Perftools light loops. The Perftools light loops module will do profiling specific to the hot loops in your code. So instead of profiling functions like gprof did, Perftools light loops is looking at particular loops, and it's going to label those and tell you what line numbers they're on. And we'll look at that in a moment. So using Reveal is a simple matter of compiling with it. So here's the Fortran compilation line I used for this Laplace code. This is the same Laplace code that you may be familiar with from the OpenACC workshops. John Urbanek and PSC have sort of popularized this code, and so I used the same code and I unparallelized it. I turned it back into a pure serial code, took out all the OpenACC and OpenMP markups, and just started from there for this demo. So it's a nice, concise example. So I compile with Perftools light loops. You do that without the linking step, and then I link in to form the final binary in a separate step. Then when I run that executable, I'll get a little info line from the performance tools on the Cray. Actually, I'm not running it here. I'm still doing my final compile. So when I compile that for this final step, the final link, I get info from the Cray compiler that it's instrumenting this executable. So it's doing a little bit more than sampling. It's marking these loops up so that later it can find these loops as things that were sampled and profiled. Then we get a batch job and run the code as usual. Since it's been completely unparallelized, I just did an app run -n1. There's no threading. Once the code is run, you get this CrayPat Lite performance output showing you that the Perftools have done their thing and they're recording some data. So you get a lot of good metadata here. It's going to note how the code ran, whether or not it was threaded, times, the kind of system, CPU, a lot of things so that you could repeat this or compare it to a different system later. A little bit of text output. You'll notice here in the text output now we're looking at loops, not function calls. And then some suggested things to do next. So the suggested thing that I did next is do the graphical analysis, which is this command. So the app2 is another piece of the Perftools. It's called Cray Apprentice 2, and that's its shorthand name. And it opens up a GUI. So this is in a job, and then back on a login node where I've exported my X display, I run app2. So here's a couple views of what I see from Apprentice 2 after running that code. Let's see if I can zoom in here a little. There we go. So this is a view of like the text info, and this is a little better layout of that table, and you can see percent time by loop, which is what that Perftools light loop is doing for us. Here's the overall GUI view. This is nice. I like to keep these around. They make good presentation fodder if you need to make a slide showing people that you profiled your code, or you want to give something to your PI, giving them like a high-level overview. This is what I expected to see from the Laplace code. It doesn't do any communication because it's pure serial. It's been unparallelized, so it just computes. And so 100% of the time goes to computation. There's no issues with load. Memory high watermark is shown there. And then this is a little snapshot of my first screen of reveal. And we'll look at reveal here further down and how I invoked it, but I'll just show you what that looks like. So reveal shows me this loop level information and the counter information together in a GUI. It's giving me loop trips, time. It's predicting what we could possibly do with OpenMP on this loop. So that's kind of a hint at what might happen next with reveal. Let's take a look. I'm just following the man page for reveal and the recipes here. So I create a program library. That's just another way of invoking the compiler. And when you do it this way, it instruments your code for Reveal to do the OpenMP markups. You don't have to run the code again. You just create this program library, and it does a bunch of extra housekeeping for Reveal. And then to get that previous opening screen from Reveal, I launched it this way. Reveal is the command, and then the directory to your program library, and the directory to your performance data from your Perftools Lite loops. And so here's another step in Reveal. So I highlighted a loop, and then I right-clicked and I said scope this loop. Actually scope this set of loops. And what that does is it's telling Reveal to analyze those loops for potential to parallelize. Are there loop dependencies? Are there things in a loop that are going to be an issue for OpenMP? Or is it a data reduction? Is it a max or a min that we're trying to do here? So doing the loop scoping is part of the automatic parallelization. This is what that looks like. After the loop is scoped, there's a really useful button here. Down here, it says insert, it says insert directive. When you click insert directive on that outer loop scope, up pops an OpenMP directive. So this is the OpenMP code that could be inserted above that loop. Actually not code, it's directives to the compiler. It can be inserted above that loop, and it will parallelize that loop if OpenMP is turned on. You can save that, which is what I did here. So that's just another button click and reveal. And this is all in the help and man page. So I saved it, and now you see between lines 54 and 55, those OpenMP directives and a comment has been inserted that says Cray Reveal has parallelized this loop this way. And so, it's figured out what should be private, what should be shared. It didn't do things like set up a schedule for OpenMP. If you need to get fancy like that, you still need to come back in here and be an OpenMP programmer and take the reins yourself. But this is a great start. The other thing it's a great start on is OpenACC. If you didn't know what to do with OpenACC, OpenMP sort of translates to OpenACC almost in a one-to-one fashion. So you now have some ideas of what you might do if you were going to send this loop over to the GPU. So I saved that, and that's now in the file. Just a little info box about how I did that. It was just file and save in the Reveal GUI. So I ran that back through the compiler, and I wanted to see what happened with the compiler with this OpenMP code. And if we look at this compiler listing, we'll see further down here. Hold on a moment. What I'm looking for is this line that says multi-threaded. So a region starting at line 61 and ending at line 68 was multi-threaded, and that's that outer loop. Now, the people with the very sharp eyes and the mathematicians in the room are going to say line 61 wasn't a loop. Let's just go back up there and look at that. It's line 61 says end do. I did not show you the line numbered. So when I ran this back through the compiler, line 55 is now the comment line. 56, 7, and 8 are the OpenMP directives. Things got renumbered internally as the compiler sees them because these directives were inserted. So that's why our numbers are off a little bit. But that 61 is that outer loop. So I ran this again with threads. I ran 8 threads. And I got a speed up of a couple times. So I did not get an 8 times speed up. You typically don't get a linear speed up with OpenMP. But I did see a speed up from this exercise, and I did not write any code. Cray wrote the code. So, magic? That's for you to decide, but fairly useful tool. Also, here you'll see that I use the time command. I like to put time in front of things. It's free if you don't have a nice accurate wall time using MPI W time or whatever in your code, which we wouldn't for this because it's serial. It's just handy to put time in front of things, and then you get the output from time. You can read more about this. These are the man page screenshots from Reveal. So if you do man reveal and scroll down, you'll get the steps that we used in this demo. So those will look familiar to you. That's what we did up above for compiling. More information about the Perftools light loop and how it works with the program libraries. And then Reveal itself has a help screen. I've shown you that here. If you just go to the Reveal and Help, you'll get tips on how to use the tool. So there's not a big web document or anything with Reveal. You just look at the help, read it for 4 or 5 minutes, and follow your nose. It's pretty easy to use. Cray describes everything in kind of nice, simple terms for anybody to follow. So I really like using this tool. I have used Reveal both to put OpenMP into code, but also to check OpenMP that is already in existing code. So I've taken professionally coded OpenMP from highly skilled teams and developers and just double check their work with Reveal. And I've compared their OpenMP directives with Cray, seeing if Cray could make improvements or if it came up with the same directives. And on one of the Better Codes applications that I tested this on, the Cray Reveal OpenMP was almost a 1-to-1 match to professionally written OpenMP by a skilled developer with decades of experience.
We have a question.
Yeah.
Was Reveal's prediction of 30 seconds of speed up fairly accurate?
It was a little optimistic. But still in the neighborhood, I would say. Here's our web page on using Reveal with OpenMP. It's part of the Blue Waters documentation, so you could also go there, and that would give you the step-by-step on how to do this. So that's a nice Cray tool that does performance. And then I've thrown in one little bonus here at the end. But you are a Python programmer. Actually, I'm turning myself into a Python programmer. Old dogs apparently have to learn new tricks if they want to keep their job. So Python, it's here. It's the future. All the cool people are using it. All the young people are using it. Blue Waters has it. There are a lot of Python modules there for you. You can look at the different modules with module avail BWPY. We're seeing it on the support side. It's in job scripts, workflows. So you may as well spend a little bit of time to see if you're running it efficiently, especially if you're running a lot of Python. If it's in lots of ensemble jobs, or you're just using it frequently. Again, Blue Waters is a big scaling machine, so you may think, well, it's just Python, and it doesn't take much time on my laptop, but if you're running 100,000 of them on Blue Waters, that's the point at which we say, well, performance kind of matters. So there are things you can do for Python, and let's take a look at that. So I've put the graphic up here for Python because this is Python stuff. There's no Cray magic here. This should work on most Python implementations, Linux, Windows, Mac. If it runs Python, you should probably expect at least to do the C profile example here and have it work. It'd be the rare Python that didn't have the C profile module included in the build. Then the next example is typically one you'd have to add for the line profiling. So here's how the C profiling goes. It's really complicated. You have to add -m C profile to your Python execution. Yeah, that's it. You're done. You've now profiled Python. When you run it that way, then you get a .profile file generated. So I added an output to name it. And then you do post-processing, kind of like you did with gprof. You run a separate command. So in this example, after I ran my Python and profiled it above in app run and a job, then I ran Python separately and ran these Python commands. pstats looks at the profile, and the psort stats here will print it. So here's an example of a Python code that I profiled this way just recently. So my assignment for this code as a programmer was to build a little Python script that will map globus identities to local exceed system identities. And because this script is likely to be deployed across exceed later, I care about the performance. I want to make sure that the performance isn't particularly slow, and I also know what parts of the code are consuming the time. So I did the commands above on this little short Python code and got the output that you see. So let's just zoom in on that a little. It's kind of a flat profile, a lot like what you saw from gprof. The Python community is trying to sort of mimic the kind of functionality that you could expect from gprof. So different lines, some of these are in my code, and some of these are in modules that my code calls. So xdctb was my code, so I had a main, I had a genmap file. You can see those showing up and the number of calls. And then there were other calls that were in Python modules, like going out to the web, that's socket, and the requests library. So this all looked the way I expected, and I was happy with the performance. But I was able to verify things were going the way I thought they were by taking this little extra step. The other profile option for Python I'll show you is the line profiler. So this is a separate module to bring into Python, It's not in a lot of default Python installations, but it's easy enough to get. You can load up your own virtual environment, which creates your own spin of Python, and just go install it, as I've shown here. So it's about as simple as pip install line profiler. That'll go out and get the line profiler package for you. I want to scroll to the right. Let's see, or zoom back out a little here. So a key part of this with the line profiler is you instrument your code. So the C profiler was like gprof, you just ran it. You just add that extra module above. You ran the C profile module, and you got a gprof kind of output that you could inspect with the Python profiling tool. Here, with the line profiling, since we don't have a compiler in Python, you get to be the compiler. So, well, you get to be the performance tool. You go in and figure out which Python routines in your code you'd like line profiling done for. Otherwise, I guess you mark up the whole code and get everything, but that might be extreme. So you go in and you put the @profile in front of one of your definitions for a function. And then that routine, when it runs, will get line profiling information. We'll take a look at that here. So the usage is kernprof to invoke the line profiler, because it's going to profile the function kernel that you mark up with @profile. And I've just shown you some of the usage info from that. And then the way it was called is down here. So after I marked up my code with the @profile, I ran this. And I put kernprof-l in front of the launch for that Python script. Then when I was done with that and the execution was finished, then I ran the line profiler command to generate the line profile output from the resulting kernprof run just above it. So kernprof generates this yourfile.py.lprof. That lprof is the kernel profile, line profile. And then when you run this second Python tool, python-m line profile, it gives you the Python line profiling output. So here's what that looked like. So the use case here is we've written up a Globus online endpoint monitor and error detection script. So this sits behind Blue Waters and watches Globus online transfers. It's using the Go API for Python. And when we first implemented this script, I had really nice performance out of this script when I ran it with the NCSA nearline endpoint. I was happy with it. I thought, well, okay, good job me, I'm done. And then a few days later, I ported this script to the Blue Waters endpoint, and it was slow. It was dog slow. It was get up and go get a cup of coffee slow. And I didn't like that. And I thought to myself, what's the difference between NCSA Nearline and NCSA Blue Waters? Well, one big difference is Blue Waters at any point in time is doing a lot more Go transfers. So I kind of had that in the back of my head as I started into this. And so I did, at the first cut, the function gprof style profiling up above with the cprofile module. And that pointed me to one routine in the code, and it was the routine I suspected, but I wanted to see why that routine was so slow, because I couldn't see it by just eyeballing it. I eyeballed the routine, and I'm like, well, I'm not really sure. So I did the line profiling, and the line profiling showed me this. So I had a line here that was being called frequently and taking a massive amount of time. And that's this T-client endpoint manager task list. And that kind of does what it sounds like if you've never seen the Globus Online Python programming interface. That gets you the task list for an endpoint. And that was just taking forever on the Blue Waters endpoint. And so I stared at that for a while, and being focused and zoomed in on that line sent me back to the Globus API documentation. I'm like, okay, can Globus help me write this line in a better way? And so I stared at their docs for 10 or 15 minutes, looked at more examples. I'd have never done this without profiling. So, profiling led me here. Stared at their documentation, and sure enough, there was a better form of this query. You'll see here there's a second if statement. There's an if statement following this really long-running time statement. And this if statement checks to see if the status is active for a particular task. After working with the API documentation, this is the different way of writing that. So instead of testing it with an if statement, we were able to use the API in a much better way and tell the Globus Online service and the back-end servers to filter just for active and only return that data to me. So instead of getting back all of the tasks, this only gets returned to me the active tasks. And look at the magnitude of the time. So this number is not like this number. It was 100x speed up. This little Python, one line, ran 100 times faster after using a little bit of Python profiling and going back and being led to the documentation. So here are some references on that. We have Python profiling documented on Blue Waters. Here's the piece of code that I profiled above if you are curious about using the Globus Online API and the docs for the Globus API. This is not a Globus infomercial, but I just thought I would add that for the curious in case you wanted to see the context where this was used. Now, the keen observer will notice that my Python profiling page did not include an HPC example. And I'm going to let a little bit of my old man steam out of the box here. I didn't put that example in because if you're running HPC code, I don't want you to use Python. I want you to use Fortran, C, or C++. I did put examples in here of Python being used the way it was meant to be used, as glue, as middleware, as things helping with a workflow. And again, there are enough use cases of this on Blue Waters, and we see it used all the time, that we want you to spend 10 or 15 minutes profiling your Python code if you think it's warranted. If you're running it at scale and it's running frequently, it's probably worth your time to just verify your Python runs the way you think, or you might find a surprise, like I did, hiding down here in one line of code. So back to my overall agenda. I think I've covered everything I wanted to for the day. So we covered two tools that were widely available, or two techniques, profiling Python and gprof. Those should work anywhere. And we covered one very cool tool on the Cray that can do some of your parallel programming for you. Hey, if you're a grad student and you use Cray Reveal under Cray and make something go really fast with OpenMP, you can take an extra couple days off and tell your PI you're really working hard on it. So that latte is on us. Thanks for watching, and good luck with your coding.
Well, thank you, Galen. We'll take a few moments here for people to pose questions, either on the YouTube chat or through Slack. If you have questions, feel free to post them, and we'll address them right away. This has been great, Galen. You included a number of references. Are there other ways for people to learn about the performance tools that you might recommend?
A Google search on performance tools and programming will get you a lot of results. When I'm looking for those tools myself, I like to filter and look for pages that go with big HPC centers like NCSA. It's kind of funny. It's not uncommon for me to go searching for performance tools and find documentation that I wrote. So that's not always helpful to me because I'm trying to learn something new. But I like pages from Lawrence Livermore, the DOE Labs, NERSC, Argonne. Those are all good references. So if you look for performance tools and then look for big HPC centers in the set of results, you're usually on the right track.
Okay, thank you. We have no questions posted yet, so if you have a question, go ahead. But otherwise, I'll ask you all to join me in thanking Galen for his tremendous presentation. And the slides will be posted. I think there's an update to the slides that will be posted shortly, and we'll let you know when the video is available. The two next upcoming webinars, November 7th, an introduction to NVIDIA Insight Systems, another performance analysis tool, particularly useful if you're using GPUs. And then November 21st, getting started with WDL and Cromwell for workflow management on multiple platforms. With that, we thank you for joining us, and we look forward to your recommendations, suggestions for future topics that would be of interest to you. Thank you again, Galen, and we'll see you again next time.